We're now going to put the solo model on a spreadsheet. And the first thing that we'll do is we'll use this formula to compute the steady state capital stock. And then we will derive all the other steady state values accordingly. Now, once you put it on a spreadsheet, of course, you're going to have to assume some parameter values. And so what we're going to do is use the ones in these notes. These are not completely arbitrary. Alpha equal to 0.36 is consistent with empirical estimates of what the share of income is that goes to capital. N equal 0.01 means that there's a 1% growth in population per year. A savings rate of 20% is a bit arbitrary. That varies quite a lot in the United States. Depreciation of 10% a year is quite consistent with data. And the setting of z equals to 1 is completely arbitrary, but shouldn't bother you. We can vary that, and we will. So with those numbers for parameters, we get these values for steady states, as I will show you shortly. Now, the other thing that we're going to do here, though, is we are going to use this formula to generate time path for capital. And once we have a time path for capital, so again, you need to have parameter values and you need to have some initial capital stock, but then this thing generates an entire time path for capital. And once you have that, then of course you can use these equations to get time paths for output, for savings, for consumption, and so forth. So that's what we're going to turn to now. So here's a spreadsheet, and the savings rate in the notes was 20%, so I'll change that to 0.2. And we have a depreciation rate of 10%, savings rate of 20%, alpha equals 0.36, TFP is 1, and we have a 1% population growth rate. So I hope most of you know how to use the spreadsheet. For the capital stock, what we have here is we simply are using the formula S times Z divided by N plus delta, all raised to the 1 over 1 minus alpha. And then once we have that, we can compute steady state output as just Z times steady state capital raised to the alpha. Steady state savings is just S, the savings rate, times output. And consumption is just 1 minus S. Okay, and then what can we do? Well, what we're going to do here is we're going to start the capital stock at 1. This is completely arbitrary. What you should realize is that when you start it at 1, you're starting below the steady state capital. And what that means is that over time, the capital stock is going to grow and eventually equal the steady state capital. We arbitrarily set the initial capital stock to 1. And then what do? Well, we just use the model. So output is just YT equals ZT, we're setting Z to a constant of 1, equals KT, well, KT is 1, KT minus 1, KT, sorry, is 1, and that gets raised to the alpha. So that gives you output. And of course, it's just going to be equal to 1, because you're raising 1 to the alpha and multiplying that by 1. Savings rate is 20%, so that means that savings is 0.2. Investment equals savings, investment equals 0.2. But now we can compute what the new capital stock is. And how do we do that? Well, we use that formula. We have the KT plus 1. If you go back, and you should be looking at your notes at this point, we have that KT plus 1 equals 1 minus delta over 1 plus N times KT plus S times ZT divided by 1 plus N times KT to the alpha. And that's what this number is. And then, once you've done that, you can then just, and this is in the first period, you can then just copy this stuff down as far as you want to go. I think that's plenty far. Let's see how far did we go here. Create some more numbers here in the first column. So these numbers we can interpret as years. So I guess we went out 413 years. And then ultimately we want to look at growth. And so in this column, what we have is 100 times the log of output minus the log of output in the previous period. And that gives us the growth rate of output, which we can go extend out. And we know that that thing's going to have to converge to 0. Okay, so we can then create some plots. And I already created these earlier. What we see here is that capital starts, well, I didn't plot the initial value of 1. That would be over here. But capital grows over time, and it ends up hitting a steady state of a little more than 2.5. Output is basically just going to mirror what's happening to capital, because output is just z times this path raised to the alpha. And if we look at growth rates, so a growth rate of output is really going to be just the slope at every point in time, right? That's the change in output. And we know output flattens out once it gets to the steady state, and therefore we know that the growth is going to have to be 0. But here's a picture of the growth rate of output. And sure enough, this is a model where growth rates go to 0. And the reason for that is we do not have any growth in total factor productivity. And so, as we will now turn to discuss in the theory, the reason that you get no economic growth in the long run in the Solow model is because of diminishing returns to capital. But what you can do once you've created your own spreadsheet is you can vary the parameters and see what ends up happening to both the steady states and to the time paths.